Hello, this is my project for tilting solar panels. All right, so for this project, basically, we have a few assignments, but the whole thing is based around the idea of a formula. Specifically this formula. And basically the idea in this formula is we have two vectors, basically the information from two sets of vectors, and basically being the area of the solar panel and its vector. And then we have u, which is basically the vector of the sun. And then finally we have the value 900, which basically equals power density. So watts per squared meter. So we basically use these three values to calculate roughly how much energy is being generated by a solar panel. That is the general idea of this formula. So in our first example, we are given a few different parameters. We're given 4 points, which make up the solar panel, and then we're also given the vector of the sun. So the example that we are given for the first one, I mean, you could technically pick anything, but I just wanted to use what our professor has given us. So the first example is 3, 3, 3. X, Y, Z. I'm just kind of giving those points there so we have a general idea of what's going on. That is the vector of the sun. And then we also have the vectors of the solar panel, which are made up of 4 points, but to make it really simple, I converted them into just 2 sets of vectors going from the origin. So we have, for the first one, it's on a flat surface, so it's just a simple 15 wide in X, and a 25 long in Y. So those are the length and width vectors, basically. So to visualize that, I will draw it as well. So here it is. So that's our solar panel vector. And then the vector of the sun is coming in at a 45-degree angle from all sides. So to view it as a 45-degree angle from all sides, it's specifically this value right here, which is 3, 3, 3. Technically, it can be any value, any value as long as they're all the same number. So it could be 1, 1, 1. It could be 5, 5, 5, 10, 10, 10. Really, all that's going to be affecting is the magnitude or the size of it. But really, what we're doing here is we're not using the magnitude of this vector. What we're really doing is we're using it only for the direction of the sun, because the magnitude has already been defined by this value of 900 in our formula. So I will go ahead and press on further. So to do everything first, we need to calculate everything out of this formula. First, we need to take this vector and turn it into the value of n. So the value of n will equal the cross product of w and l. So to do that, we have to lay out w and l in the I, j, and k format. So 15, 0, 0 for the width, and then 0, 25, 0 for the length. And then we have to put that into the formula. And then we have to cross multiply them. So doing it in cross product, I will continue drawing it. Minus I minus j, and then plus k. So yeah, you take only, for I, it's only j and k, of course. For j, it's I and k. And then for, of course, k, it's going to be I and j. So when we multiply and do everything that we need to do, we find it to be 0i, minus 0j, and then plus 375k. So now we have all these values, and then we can also convert that. But really what we're doing, if we add all these together and we just ignore the individual variables that each are labeled by, we also get our area of the solar panel equals 375 meters squared. So we have that calculation, and then we also have the calculation as the cross product of the two vectors as another vector for itself, which is just 0, 0, 375. So that we'll basically use this as our n. And then to find the u portion, we need to find the vector of the sun's ray, the directional unit vector, aka just the direction, not the magnitude. That is what the unit vector is for. So unit vector, so that'll be u in the formula. That's what it stands for, is unit vector. I believe n stands for maybe net area. I think, I'm not sure what n stands for in this, but we know that u can be associated with unit vector. So the formula for unit vector, u equals magnitude v, or equals v over the magnitude of itself. And when we do that, when we have the vector over the vector over the general magnitude of itself, that will convert it into the simplest vector possible, where everything is equal to the lowest possible value that will allow it to be multiplied into the formula. So then it's just a direction, there's no real influence of magnitude, which is where the 900 comes in. So let's see. So we know that magnitude of v and the vector of the sun, again, is v. So the magnitude of v, we have, to find that, we have to do the square root of each of these values added, each of the individual coordinates added, squared. That equals the root of 27. And then we can simplify that further to 3 square root of 3. So let's see, once we have that value, we then have V divided by 3 square root of 3, which equals 3 over 3 root 3, comma 3 over 3 root 3, comma 3 root 3. So all these cancel, all the 3's cancel, and then we become left with this answer right here, this set of coordinates as our unit vector from the sun. All right, so we have our u, unit vector, and we have our n. So now what we can do is we can do the formula, which basically is the dot product of u and n times 900. So here we go. So we have the vectors we have the vector n times the unit vector times 900. So when we multiply it by 900, we'll have 900 in the numerator. So that becomes 900 over root 3 on all of them, on each axis. And then what we can do is we can do the dot product of these two. And what happens is basically we do the dot product and we will get the individual value which calculates the power. It will no longer be a vector, it will now just be a single unit. So we'll have 0 plus 0 plus 375 over 1 times 900 over the root of 3, which equals, let me do it on my calculator, 337,500 over the root of 3, which equals, I'll do that on the calculator again, 194,856 watts. And the reason why the reason why it's just watts is because the 900 is already in watts per squared meter, and the 375 is in meters squared. So what happens is those two cancel out once they're multiplied together. So that's why we only have 194,856 watts. All right, so now we know exactly how much energy is being generated by the sun at this angle. That is our answer. Now, we want to find exactly what the angle is. So to find the angle, we will use another formula, which also uses, like the previous formula, it also uses the dot product. So it's going to be the inverse of cosine times this magnitude times the dot product of the two vectors over the magnitudes of the two vectors. All right. Now, let's see. The magnitude of n is really easy to calculate. Technically, we already had the magnitude of it. Well, we didn't have the magnitude of n. We had the vector of n. But to find the magnitude of it, aka that area from before, we can also just do this. So we're just going to do that really quick. I'll just get the magnitude of both. So the magnitude of u we already know is the square root. We'll just do the magnitudes of both. So we'll do the magnitude of u. We already did the magnitude of v to create u, so we have to do the magnitude of it again. That's what we're doing. So 1 over square root of 3 plus 1 over square root of 3 plus square root of 3. That will equal root 3 over 3, and that just equals 1. And this makes a whole lot of sense, because really we wanted the vector to equal 1 initially. So since we converted the vector of the sun v into the unit vector, its magnitude will be equal to 1, and this proves that. Because really, the magnitude is 1 because it's for direction, not magnitude. So that's the main thing for the reasoning behind that vector u that we converted from the sun's vector. As I said before, this just proves it further. All right, and then the other vector that we're going to compute here is n, or magnitude of the vector is going to be n. So that's going to be equal to 0 squared plus 0 squared plus 375 squared, all square rooted. And that will just equal square root of 375 squared, equaling 375 meters squared. There you go. So now that we have those two, we can go right ahead and just do our formula. So we can go ahead and do the dot product between u and n as well. Let's do that. So the dot product between u and n. So that's going to equal I have to look back to figure this out. Yep. So yeah. Root 3, all those, times that, times our other value of n, which is that's going to equal 0, 0, 375 over root of 3. So there's the top of our formula. and then we have the bottom. So we go ahead and divide that all by 1 times 375. So then what happens here? Well, the zeros just become zeros, so we kind of ignore those. And then it's just 375. So all that happens now is we literally have 375 over the root of 3 over 375. And so those two 375s cancel each other out, and we're left with cosine. We're left with the inside, what's inside of the parentheses now, which is going to be 1 over the square root of 3. So cosine inverse 1 over root 3, which equals, let me do the math now, inverse cosine 1 over root of 3, 54.736 degrees. Now, what we need to do further, though, is we're not done yet with the angle. We still need to find the complement of it. So to find the complement of the angle, between n and u, we have to subtract the angle of the angle that we just calculated. From 90 degrees. So to do that, we'll do that right here. So 90 minus 54.736 equals 35.264. So that is our final answer for the angle between the panel and the sun's ray. Now, if we're taking the complement, the idea of this whole thing is that we really want the difference between the two to be as small as possible. Oh, well, I wouldn't say that. But, well, basically what I'm saying here is that the angle that we generated, that we created first, we wanted it to be small. But when we do it and subtract it from 90, we want it to be as large as possible. And the reason why is because this angle is basically telling us how perpendicular we are to the sun. So really the ideal thing that we want is a perfect 90-degree angle. And the reason why we want that perfect 90-degree angle is so now we get all of the sun's rays, because what's happening is the sun is traveling down toward us in this environment. The sun is traveling down toward us in a perfectly straight line. Photons travel as a perfectly straight line, and it's demonstrated when you use lasers, when you use flashlights. They all generate a beam of photons. So really what happens is photons come down like that. It's like when you pour sand or when rain falls. They're all falling in the same exact direction from where they were projected from. And they're hitting the surface of the panel. So what we want to do is we want to make sure that that angle is basically as small as possible. Now, to make this a little easier, I'm going to do a two-dimensional demonstration for this concept. So let's just say that I have a couple of panels facing different directions, right? And let's just say that I kind of cut them out a little bit, and they kind of all look like really terrible versions of, just poorly drawn versions of Nevada. You know? I just kind of cut them all out. Well, here, I'll make this one a little bit longer just so it's kind of equal to the length of the panel that I have. So I'm just showing you a few examples where the angle of the solar panel is different. So notice how the flat one, we have the entire surface area of the sun. Sorry. The entire solar surface area right here. And the entire surface area of the bottom, where the solar panel is, are equal. They're completely equal. And they are perpendicular with each other. See that? They're perpendicular. They both have perfect 90-degree angles on each side. They are perpendicular. The ray, the vector between the two, the solar ray vector, is perpendicular to the surface of the solar panel perfectly. So that means all of that rain, every little drop, every little photon is going in the same direction, and they're all coming down and hitting the surface of the solar panel. So the surface of the solar panel is being maximized. It's being fully utilized in this scenario. Whereas when we have the two angled ones, notice how this surface area is significantly smaller than this surface area of the solar panels. So what that means is we have a significantly lower amount of overall photons hitting the surface. So because it's at an angle, less power is being generated. So therefore, a higher difference in angle means less power is being made. So really what we want is we want it to have the lowest possible difference between the two. So if it's at a perfect, if it's at the perfect perpendicular, we're going to have all the surface area being utilized, so all the power that needs to be generated by that side is being generated by that side. So overall, that is the most optimal method to do it, is to just have it perfectly perpendicular with the solar panel. So now with the second problem, we can demonstrate this further. So we're going to now do the second part. So the second problem is going to be with an angled panel. So in this scenario, we have the same exact vector of the sun. And so the magnitude is going to be exactly the same. So then u as the unit vector is still going to equal the same exact value. All right. And then also, the only difference here is that our value n will be different. So the area of our solar panel will be a little different. The area is going to be the same, but it's going to be the angle that's going to be different. So here's the panel as the most probable orientation, right? So I have the two area vectors of width and length again. And this time, length will be exactly the same, basically. Well, it's going to be the same exact length. So that vector has been unchanged. The width vector, however, has been changed. So now the panel is at an angle, right? So as you can see, it's going to be still be 25 meters wide. But now the panel will be at that angle. It'll be angled upward. And so in the width, it will have to be corresponding to that. So what we had to do was we had to see that vector and these were from the sets of points that were given. So we have that vector, and then we have the other vector, which is the subtraction of the other points. So that one becomes negative 12, 0, 9. So now we have those two, the width and the length vectors, right? Now we can go right ahead and create the value n. So we're going to do that. So now we do these cross products, and this is what we get. For I, and then j, and then k. So now what we do is we multiply them from this top to bottom. Well, we do left to right. So yeah, so we have 25 times 9 subtracted from 0 times 0. And that's just going to be 225. Minus 0, so it's just 225. Excuse me. And then 0 times 9 is 0, 0 times negative 12 is 0, so that's 0. And then 0 times 0 is 0. So 25 times 12 is going to be, well, we already know 25 times 4 is 100, so it's literally 4 3 times, so it's 300. Oh. So there's our n vector. So we can just rewrite it as a vector, 225, 0, 300. All right. And now, since we have both vectors, we can now do the dot product and multiply by 900 to find the value. So let's go right ahead and do that. So from what we remember, 900u, so it's literally just going to be these two values. So it's going to be 225 times 900 over root 3, comma, 0. Sorry, not comma, but plus 0, plus, because we're just doing the magnitude overall in this dot product scenario by adding all the parts of the vectors together as well, times 300 times 900 over root 3. And once we do all the math behind that, we get 225 we get 225 times 900 plus 300 times 900, and that equals 472,500. And then we can put that all underneath the square root of 3. So that gives us our watts now. So we already had the meters squared cancel out the other meters squared in watts. So now it's going to be the watt value again. And now we get the value of 272,798. So as you notice, as you can tell, this value for the angled panel is larger than the value from our other panel that was completely flat. So what does this mean? Well, it seems like it basically means that because, well, let's think about it like this. Both the panels, and I checked the vectors. I did a measurement just to make sure. Both of the areas were exactly the same. 12 and 9 were the dimensions for the separate parts at the angle of the vector for the solar panel on the other side. So we had the side that was 25 long, but the side that was angled, we couldn't really tell. You'd have to do some basic math to figure that out. So it was 9 and 12. So 12 squared and 9 squared. Basically, we just did the simple Pythagorean theorem. So 144 plus 81, 225, and the square root of 225 equals 15. So we know with basic math that the area is the same. So the only thing that could increase this value then, right, is what I proved before, was the difference in angle. So it must be closer in angle. So we're going to go right ahead and prove that they are closer in angle now by using the same formula that we did before for doing the angle of, basically the angle between the sun. So cosine inverse of u dot n over magnitude of u, magnitude of n. So now when we do that, we go right ahead. Oh, whoops. We go right ahead and we do the dot product of those. So let's just do that really quick. Almost put 375 there. All over the magnitude of u and n. And to find the magnitude of n, we need to do that really quick. So what we're going to do is, of course, we're going to find the magnitude of n. We already have the magnitude of u. We found that before. The magnitude of u was equal to 1. So the magnitude of n is equal to square root of 225 squared and 300 squared, which equals, let me calculate that real quick. $375. Well, would you look at that? The denominator is exactly the same as before. So now we know that the only thing that could possibly have changed is this value right here. And that is the only thing that changed. Nothing here changed, nothing here changed. So yeah, it literally is only the angle between the two that has changed and has led to our increase in energy generation. So let's go right ahead and find the answer real quick. So let's see. That is so we've got those values multiplied together. So we can just multiply those values and add them all together. So it is 225 plus 300, which is 525. So now it's just 525 over the square root of 3 over 375. So now what we do is we go right ahead and put those values together. And we solve. So let's go right ahead and do this in my calculator just so it's a little easier. 525 over the square root of 3. All right. And then we divide that answer by 375. So now that is whatever this variable is, I'll just put it in. 0.80829036769 in my calculator. And we're going to go right ahead and put that in the cosine inverse of the formula now of that answer. And that equals 36.071 degrees. All right, so now we can subtract from the complementary, and we could find the complement of that angle. So let's go right ahead and find the complement. Minus our angle delta, which is 6.071, and that equals 53.929 degrees. So basically, this is showing that we have a, how would you say it? We have a more, I guess how you could say it is we have a more perpendicular angle to the sun with this angled panel. Okay. So now that we've basically proven that idea, there's a few other things that we can think about. So now that we know this, let's think about one thing, the first thing that our teacher said. He said, what is the worst angle possible? And I had to think about this for a second because both sides of the solar panel are conducting in this example, which is not necessarily true for solar panels. But both of the sides conduct when they're facing sunlight. So I had to think about it in this way. Since I view photons as traveling, in a straight vector, that means that the goal then of this whole thing is to be perpendicular to the solar panel with the sun's ray. And when we do that, we generate energy. So how do we not generate energy? Well, we simply do the opposite. We don't want to be perpendicular. Instead, we want to be parallel. So if we did a parallel solar panel with the sun's rays, if we just had a solar panel sitting on its side and we had the sun's rays coming down, in a perfect world, without like all the other things to think about, it wouldn't be touching the panel at all. It would only be touching little sides of the panel that, we're going to, for the sake of argument, we're going to assume the really slim sides are non-conductive. So since they're not touching, that basically means that no power is being generated in a perfect world. Now, in the real world, if you had a panel lying on its side at high noon, you'd definitely still be generating some form of energy. If we had it at a perfect angle with the sun, I would think that there's all the surrounding landscape has, it'll have sunlight reflecting off of it. So you will be generating a little bit of power, not as much as you could, but you'll be generating a little bit of power still. But in this example, we're going to say that, since there's nothing here, that proves it, that there's no way for it to be touching. So let's do an example. So I've got the angle here. I'm just going to use a very simple two things here. I want to change some variables just to make these examples more easier for myself to explain. So I wanted to put the sun at high noon. So that means that our sun's angle is, straight down. Basically this way we don't have to, do a bunch of other steps for calculating it. I couldn't exactly, I tried to spend some time figuring this out, but it was really making me go nuts. Maybe we'll learn it a little bit later in this class of how to actually calculate. I guess you would do something kind of solving for variables. You would be trying to figure out what the optimal angle is for the solar panel. So if we could have, tilted the panel, we could find a way to tilt it. But what you really want to do is you want the solar panel to be parallel. So we're going to go straight down. So our vector in this example is going to be 0, 0, 3. That way it's going straight down. So it's only in the z-axis that it's 3. So basically, if I've showed it to you, it would be like this. You'd have your things, and the sun would literally just be right here. So yeah, so that's what we're going to do with that part. And then the next part that we're going to do is we're going to put the solar panel on its side. So I had to think about this too. At first I thought, hey, if I just put the solar panel on its side, it doesn't matter where I put it. So I tested that. And when I did that, I tried moving the solar panel 10 away from the origin and putting it up right here. I tried putting it up 10 paces from the origin, 10 meters from the origin, and putting it up on its side. And what happened was really interesting. I got a negative value. So I got a value still, but I got a negative value when I did the the total power calculated when I use the power formula. And I believe the reason that I got that was because this formula is actually very similar, surprisingly. I found this watching an organic chemistry tutor video the other day, a tutoring video. He had a thing that was for the volume of parallelepipeds, and a parallelepiped is an angle, is a shape, is a three-dimensional parallelogram, just like kind of what we're working with here. If we were looking at the sun's rays intersecting with the volume here. So the cool thing is I've noticed that this formula is kind of like a volume formula for a parallelepiped, except in the z direction, we're not using, or whichever direction the sunlight is going, we're not using, we're using a fixed magnitude. There is a fixed constant magnitude from the sun, which is the 900 watts per square meter, which is supposed to be basically the 900 square watts per meter that's going to be projected onto the area of the solar panel from the vector that's being projected out from the solar panel. So they're intersecting, and we're calculating that. And I found that kind of interesting. So, but anyway, yeah. So I found that like you kind of have to have the vector of the sun and the solar panel in the same area. They have to both be touching, basically, for you to calculate things accurately. Because that's kind of like, oh, well, it's negative. I mean, that kind of doesn't make sense. But it kind of does because it's the other side of the panel. I don't know. There's a few little things in this solar formula that, it has to be simplistic, though. There's a lot of things that this formula doesn't take into account, but it has to be simplistic. So we're just going to have something in the same exact, in this example, I've decided to change it to make it more simplistic for the viewer and have it in the same exact area, as the vector of the sun. So the same origin. So let's see. The width and the length is going to be let me do that a little bit differently. 0, 25, 0, and 0, 0, 15, 0, or 15. And what these vectors become is basically you have something only in the z-axis. So the solar panel is only existent in the z-axis and the y-axis, and not the x-axis. So what happens is the solar panel is literally on its side, and it's in the same exact side, or it's parallel to the sun's light. That's what it looks like, right? It's parallel. So the solar panel is literally facing on its side in relative to the parallel to the sun's light. So let's go right ahead and calculate this now. So we're going to go right ahead and we're going to do the same formula from before. We're going to find n. So we're just going to do the old ijk for finding the coordinates. So we take out, for finding the cross product of the coordinates, or the vectors. And what we come up with is we have I, J, K, so I is going to be, J is going to be, and K is going to be, so these both go to 0. And then the I becomes 25 times 15, which becomes 375 by itself. So now we can convert that back into a regular vector, and so that's just 375, 0, 0. So, yeah. So the area vector of that. Now we can go right ahead and we can plug that into the u vector. So let's find u as well. We have to do that. So V equals, or U equals magnitude of V. So magnitude of V is going to be 0 plus 0 plus 3 squared under the square root. That is going to be only 3. So now our unit vector divides that. So we divide that 3 out. So V divided by magnitude of V equals equals 0, 0, 1. So that's our magnitude vector for, or that is our unit vector of the sun's ray, again, for this part. So now we will plug that back in. So let's go right ahead and do that. N times 900U. So 900U. So we got 375 times 0, 0, 900. And then we have that divided by our whatever value that we had from before. Or we don't have that divided by anything, sorry. Well, what happens is we have to do the cross product of all these. So what happens is 375 times 0 is 0, and 900 times 0 is 0. So what happens is the whole thing becomes 0 watts. So this just kind of proves that idea that I had before, that if it was perfectly in parallel, if the solar panel was lying on its side, perfectly in parallel with the sun's rays, not letting either of the flat sides touch it, then yeah, it's supposed to, in this ideal environment, create 0 watts. And now we can prove this further by calculating the angle. So let's go right ahead and do that. So let's use our angle formula. So the angle formula is going to be U dot product V over the magnitudes, N to N. And then once we do that, here's what we're about to see. So let's see. So if we do that, U times N is going to be 0, and then the magnitude of N is just going to be U, which the magnitude of U, I believe, is just 1 times N, and the magnitude of N is going to be 375. And what's going to happen is that's going to equal 0. Cosine of inverse of 0 is equal to 90 degrees. And so what happens is the complement, 90 degrees minus 90 degrees, is going to equal 0. So that means there is no angle of difference between sun and panel. Therefore, no power. So there you go. So we have no power being generated because of this. So now we know that if the solar panel is parallel to the vector, no power is generated. There we go. And now for our final part of the question. What's the most optimal way to generate power? Well, the most optimal, of course, is going to be when it's perfectly perpendicular to the sun's rays. As I said before. So we're going to do another example just to prove this idea. Let's just do a width and a length real quick, and we'll make it really easy. We're going to do the flat from before, from the first problem. And the only difference with this version of the problem is the sun's vector. We're going to make the sun's vector what we did before. I'm just going to make it even simpler. The vector of the sun is going to be equal to 0, 0, 1. So now we're going to go right ahead and calculate n. From the first problem, we already knew what n was. N is going to be equal to, when we did the dot products from before, is going to be 0, 0, 375. And we did that in the first problem. So it's going to be just like the problem from before. And now the magnitude of v for, well, we'll calculate for u. And for u, which equals the unit vector of v over v, or the unit vector, which is going to be v over magnitude v, is going to be equal to over 1.
Huh?
I am recording right now.
Oh, I'm sorry.
Sorry about that. Over 1. So that's just going to basically make it all become 1. So now we already know that our magnitude or unit vector is just going to be equal to 1. So, sorry, I forgot to do this, but you just add all these together. I'm sorry. But yeah, you add all those together, and then you do over 1, and that's just going to be 1. So our unit vector is 1. So now equals 375, and then we put 900 in the vector of u, 0, 0, 900, and that equals 37, 500 watts. So now we have a much higher wattage than before, because there's nothing that we had to divide or anything. Everything gets completed and taken. So this is literally the highest value we've generated. As you can see from the previous answers, the highest we got was 272,000. So this is significantly higher than all the other ones. So we already know we're going in the right direction. Now let's just grab the angle just to prove that this is the maximum amount of energy we can generate. So angle theta equals cosine inverse . So that, we already know the magnitude of u is going to be equal to 1 from before, from a problem before. We already calculated this. So magnitude of u is equal to 1, and the magnitude of v from before is going to be 375, because square root equals 375. So what happens now is we have the 1 times the 375, because that's all we see in both values, is we have a 1 times 375 in the top, in the numerator, between the two vectors. And I'll show you that here real quick. When we dot product these two, we just get 375. And we have 375 in the denominator. So that equals 1. And the cosine of 1, inverse of 1, equals 0 degrees. So now, when we find the complement, 90 minus 0 equals 90 degrees. So it's perpendicular to this vector. It is at a 90-degree angle. It is at a 90-degree angle to the sun. So because of that, we generate the most possible power. So there you go. That is our most optimal. As long as the solar panel is perpendicular with the sun, it generates the most power. And there we go. And that concludes.